Hello friends, I Deepak Prajapati welcome you in lecture number 12 on nonlinear partial differential equations of first order. Today we are going to discuss about one important method of solving nonlinear partial differential equations of first order. This method is known as Charpitz method, and using this method we can solve nonlinear partial differential equation of order 1. So in this lecture we are going to discuss Charpitz method, and we will see how to use Charpitz method to find out solution of a given nonlinear partial differential equation. So let us start with Charpitz method. Charpitz method is a general method for solving partial differential equations of first order but of any degree. That means we can solve nonlinear partial differential equations of order 1 by Charpitz method. So this Charpitz method is general method for solving partial differential equations with two independent variables. So we start the description of Charpitz method. Suppose we want to solve this first order partial differential equation of order 1 denoted by f of xyz pq equal to 0, where z is a function of x and y. So we have x and y as independent variables. Small p is partial derivative of z with respect to x, and small q is partial derivative of z with respect to y. So this is the general form of first order partial differential equation of order 1. So suppose we want to solve this equation by Charpitz method. So we discuss the steps of Charpitz method. The first step is you have to write your equation in this form. That means you have to consider all the non-zero terms on one side, and on another side you have to write 0. So first step is transfer all the terms of the given equation to left hand side and denote the entire expression by small f. So after finding out small f, we have to write Charpit's auxiliary equations. dx upon del f by del p equal to dy upon del f by del q equal to dz upon p into del f by del p plus q into del f by del q equal to dp divided by minus del f by del x minus p into del f by del z equal to dq divided by minus del f by del y minus q into fz. So all these equations are known as Charpit's auxiliary equations. Now once we know what is the small f, we can find out all these derivatives, del f by del p, del f by del q, partial derivatives of small f with respect to x, y, z and p and q. So while finding out these derivatives, we will consider another variables as constant when we are differentiating with respect to one variable. So after finding out derivatives, we will put their values in Charpit's auxiliary equations, and among these 5 fractions we will find out 2 fractions such that we are able to find out either small p or small q by solving those 2 fractions. So after simplifying step 3, that means after putting all these values here, select 2 proper fractions so that the resulting integral may come out to be the simplest relation involving at least one of p and q. So that means we have to select proper fractions, 2 proper fractions, such that we are able to find out at least one of small p or small q. Now after finding out small p or small q, another derivative can be found out by using given equation that we have denoted by 1. Suppose we are able to find out small p by solving auxiliary equations, we will put value of small p here, and from this we are able to find out value of small q. So once we obtain small p and small q, we have to put their values in this equation, dz equal to small p into dx plus small q into dy, and after integrating this we will obtain the required complete integral. The singular and general integrals may be obtained in the usual manner. That means we have discussed how to find out singular and general integrals in previous lecture. So using the definitions we are able to find out singular and general integral once we have obtained complete integral. So let us discuss this example to understand the method. Find a complete integral of p square minus y square q equal to y square minus x square. So first step is we have to consider all the non-zero terms on one side. So we start by step 1. We write given equation is, we write here p square minus y square q. We consider this right hand side on this side, so negative of y square plus x square equal to 0, and suppose we give this number 1. So first step is we have to transfer all the non-zero terms on one side, and we will give this left hand side, or left hand side will be denoted by function of x, y, z, p, q equal to p square minus y square q minus y square plus x square. So next step is we have to write Charpit's auxiliary equations, but before that it is better to find out partial derivatives of small f with respect to x, y, z, p, q. So suppose we consider del f by del x, then there is no x here, so here derivative is 0, here also 0, here also 0. There is a x square in only one term, so del f by del x is 2x. Similarly del f by del y is, we are having y in two terms, remaining variables are constant, so here minus q is constant, derivative of y square is 2y, and the derivative of y square is again 2y. There is no z here, so we put del f by del z equal to 0. This function is independent of z, or z is absent in this function, so partial derivative with respect to z is 0. Partial derivative with respect to p, so we have only p square. This term only contains small p, so derivative of p square is 2p, and similarly this is the only term containing small q, so minus y square is constant, derivative of q is 1 with respect to q. So now we write down Charpit's auxiliary equations. Charpit's, this we have to remember, Charpit's auxiliary equations are dx divided by del f by del p equal to dy divided by del f by del q equal to dz divided by small p into del f by del p. This is multiplied with small p, and this del f by del q is multiplied with small q. So it is not hard to remember these equations. Here we write dp, so here we have del f by del x minus small p into del f by del z. Similarly with dq we will write minus del f by del y minus q into fz. Now after writing Charpit's equations, we have to substitute all these values here. So therefore dx divided by del f by del p, which is 2 times p, equal to dy divided by small q, which is minus y square, dz divided by small p into fp, that is small p into 2p, plus small q into fq, which is minus y square, equal to dp divided by minus del f by del x. Del f by del x is 2x and del f by del z is 0. So del f by del x is 2x and del f by del z is 0, so it is only 2x. Similarly, del f by del y is minus 2y cube minus 2y, but we require minus del f by del y, so it will be positive 2y cube plus 2y. Plus 2y, and del f by del z is 0. So these are Charpit's auxiliary equations. Now we have to select appropriate fractions so that we are able to find out either small p or small q. So here these two terms contains small p and small q, and if we concentrate on this fraction dp upon minus 2x and on first fraction, then we can see we will be able to find out solution using these two fractions, because differentials are dx and dp and remaining terms are also in terms of x and p. So we will consider first and fourth fractions. So taking first and fourth fractions, we get, so first fraction is dx divided by 2p, and this is minus dp divided by 2x. So 1 by 2 will cancel out, and this we can rewrite as x dx equal to minus p dp. 2 will cancel out. Again this we can rewrite as x dx plus p dp equal to 0. So this is separable equation, so we can directly integrate. This is separable in x and p, so integrating we obtain integral of x is x square by 2 with respect to x plus p square by 2 equal to constant of integration. Suppose we adjust as a square by 2. So we know that constant of integration can be adjusted as we wish. So here we adjust it as a square by 2. So a is arbitrary constant. So from this we obtain p square plus x square equal to a square. So we are interested in the value of small p, so we write this as p square equal to a square minus x square, and therefore small p is under root of a square minus x square. So this is the value of small p. Now to find out value of small q, we will substitute this value of small p into given equation. So we will substitute value of small p in this equation. Here we have p square, so it is better we directly put p square equal to a square minus x square in equation 1 to obtain value of small q. So putting p square equal to a square minus x square in given equation 1. So here we put a square minus x square minus y square q. A square minus x square minus y square q minus y square plus x square equal to 0. Minus y square plus x square equal to 0. So you can see x square will cancel out, and we will have a square minus y square. Okay, we combine these two terms and we take this term minus y square q on right hand side, so it will be positive y square q. So we are interested in small q, so q will be a square minus y square divided by y square, and this we can rewrite as a square into y to the power minus 2 minus 1. Y square will cancel out. So therefore q is a square y raised to minus 2 minus 1. So this is the value of small q, and small p is under root a square minus x square. So this step is find out values of small p and small q. Now in next step, because z is function of x and y, we can write total differential of z as dz equal to del z by del x dx plus del z by del y dy, and we know that del z by del x is small p and del z by del y is small q. So here we have to put values of small p and small q. So p is under root a square minus x square. So we put value of small p under root a square minus x square dx plus q is a square y raised to minus 2 minus 1. A square y raised to minus 2 minus 1 dy. So now this is separable equation, so we directly integrating we get integral of 1 with respect to dz is z, integral of under root a square minus x square is x by 2 under root a square minus x square plus a square by 2 sin inverse x by a. This is the formula for integral of square root of a square minus x square. Integral of y raised to minus 2 will be y raised to minus 2 plus 1 divided by minus 2 plus 1 minus integral of 1 with respect to y is y and plus arbitrary constant. So this we can rewrite as therefore x by 2 under root a square minus x square plus a square by 2 sin inverse x by a, and this we can rewrite as a square by y minus y plus b. So this is the complete integral of given non-linear partial differential equation, where this small a and small b are arbitrary constants. Okay, so this I have to rewrite again. Z equal to x by 2 under root a square minus x square plus a square by 2 sin inverse x by a minus a square by y minus y plus b. So this is required complete integral. Okay, so I don't write again, here I directly write, which is required complete integral. This is complete integral because in this integral there are two arbitrary constants a and b, which is equal to the number of independent variables in the given equation, which are 2. So in this way we can find out complete integral of first order partial differential equation using Charpit's method. So let us just quickly revise the method. First step is you have to consider all the terms on one side, all the non-zero terms on one side, and you have to give resulting expression. We can denote this left hand side by small f. Then we require derivatives of this function small f with respect to x, y, z, p and q. So first we find out their derivatives. After that we have to remember Charpit's auxiliary equations. So dx upon fp equal to dy upon fq equal to dz upon p into fp plus q into fq equal to dp upon minus fx minus p fz equal to dq upon minus fy minus q fz. Then we have to substitute derivatives, value of all these derivatives into these equations, and to solve these equations we have to combine at least two fractions. We have to combine two fractions such that they contain at least one integral either in terms of p or in terms of q. So after solving that two fractions we will be able to find out value of small p. So here first we find out value of small p, that we put in the given equation, and then we are able to find out small q. So in this step you have to find out values of small p and small q. After that remember this formula dz equal to p dx plus q dy, and put values of p and q in this equation, and then integrate with respect to x, y and z. So in this way we can find out complete integral of a non-linear first order partial differential equation using Charpit's method. So we stop here. In upcoming lectures we will do some more problems on Charpit's method. Thank you very much.